Hello, my name is Marlene, and this is my Math 121 research project. I decided to focus my research project on the concept that we learned in class for the volumes by disk by washer method, and specifically focusing it on a volume displacement. So, um, first, I decided to focus my presentation, my research project on section 1.2 that we learned in class towards like the beginning. One of the first things that we learned, volumes by disk slash washer method. I'm specifically going to focus on the disk method. So for the disk method, it states it's like solid revolutions that are formed by the f of x, where the f of x is continuous on a to b, and f of x is greater or equal to 0. And below, I inserted a screenshot, a photo from my notes that I took in class, where the volume formula for this using the disk method would be the integral from a to b, pi times f of x squared times dx. So that would be how to find the volume by using the disk method. Next, I have the ways that it's used in the physics major. So my major is physics. I aspire to become a teacher, a high school or middle school teacher, physics teacher. But so these are some ways that the volume displacement, specifically focusing on volumes by the disk slash washer method, would be used in the physics major. So first I have mass calculations when combined with density. For that, I have the mass is equal to density times volume. This could be like for wood or metal, and you can move around the mass times, or mass equals density times volume, for example, if you want to find density or the mass. So another way that it can also be used is the moment of inertia, rotational dynamics. For this one, an example for this I have is to find the rotational inertia of a merry-go-round or bike tires, etc., anything that rotates. And next, I have the volume displacement, fluid mechanics, and Archimedes principle. This one is the one that I'm specifically focusing on, but other ways, or like a way that it's used, is to find the mass of irregular shaped objects, and for the volume displacement, and then Archimedes principle for to find if something floats or not, and the buoyant force. Yeah, that's for using the Archimedes principle. And then the last example of how the volumes by disk slash washer method could be used in the physics major would be heat conduction. Solid of revolution may represent an object through which heat flows. For this one, it's specifically in situations where the object has symmetrical heat transfer properties, and this could be like in forms of a cylinder or a cone shape. So next, moving on to volume displacement. This one is what I am focusing my research project on. So here I have a quote that I got for the definition of volume displacement. Volume displacement is the amount of space an object takes up when submerged in fluid water, most likely. The total displacement is made up of from how much the water rises, and this is a quote and definition I got off from study. I'll link the website in my source cited page. And so this method is typically used when calculating the volume of odd slash irregular shaped items. Here I have a picture, and it has a nail, a like bolt, or it's a screw of some sort that's dropped in water, and in the picture you can see how after it's dropped in the water of the graduated cylinder, the water seems to have risen, and that difference from how much from how the water was before there was anything in there to now that the um, bolt is in the water, that would be the mass uh, of the bolt. So the displacement of the water, volume displacement. And next, I have the Archimedes principle definition. This one, it's a body at rest is in a fluid. It's acted upon by a force pushing upward called the buoyant force, which is equal to the weight of the fluid that the body displaces. If the body is completely submerged, the volume of a fluid displaced is equal to the volume of the body. And this is a definition I got of the Britannica website. I'll also have it in my source cited. And this specific principle helps us explain why some objects float and some sink, or just some stay like above. Why some, and in my case, for the specific example that I'll get to, I did it in water, but it could also be used in cases like in the air. An example for that would be like a hot air balloon, like how it floats in the air. For this one, I have the weight of air surrounding the balloon is greater, so it floats. And if um, the water, sorry, the hot air balloon was a greater weight, then it would start descending. Next, I have the buoyant force. And my definition for this is the buoyant force is the upward force extended on an object wholly or partly immersed in a fluid. This upward force is also called upthrust. Due to the buoyant force, a body submerged partially or fully in a fluid appears to lose its weight, i.e., appears to be lighter. And this is a definition I got of BYJU's, and I also have it in my source cited. So for this one, the buoyant force, it goes hand in hand with Archimedes' principle, which again helps us to determine if an object floats or sinks. But the difference between the buoyant force and Archimedes' principle is that the buoyant force is always present and acting on an object, whether it's immersed partially or entirely in fluid. So now moving on to my real life example for volume displacement, and I specifically picked volume displacement by a hollow submarine hatch. So for this example, it's just a random example with random numbers, but we will look into a submarine hatch shaped like a hollow cylinder dome that is partially submerged in water. And for this, we need to know how much water it displaces, which will determine the buoyant force acting on it. We'll be using this equation for the volume. It's a modified version from the one we learned in class, but still, it's the same thing basically. Its volume is equal to pi integral from 1 to -1 parentheses r of x squared minus r of x squared, so the first one, second one, and then times the x. And we'll also be using this other equation for the buoyant force of f sub b is equal to pgv, the volume. So now we'll be using the volume by Washer method, and so for our example, we have the outer shape r of x is equal to the square root of 4 minus x squared, which gives us a semicircle of a radius of 2. And then for the inner hollow, we have the r of x is equal to the square root of 1 minus x squared, which gives us a semicircle with a radius of 1 on the intervals of -1 to 1, which is why in our previous volume equation it had the bounds of the integral from -1 to 1. So This shape will create a washer shaped solid with a dome as with the hollow center. So then to find the volume, I have the worked out integral. When you plug in the r of x is both for that outer shape and the inner hollow, it will give us a total of 6 pi. So this 6 pi is our volume of displaced water, so it would be 6 pi meters cubed or cubic meters. Next, we'll be using Archimedes' principle. We have to calculate the buoyant force. This being in a physics context, we'll be using Archimedes' principle. So for our specific example, if the water density is equal to 1,000 kilograms per cubic meters, the water displacement is volume is equal to, and the water displacement is a 6 pi cubic meters, then we will be using Archimedes' principle formula, the previous one that I had mentioned when in slide 7. F sub B is equal to PGV. So when we plug in our values for that, it will give us approximately 18,478 newts. So that would be our total buoyant force. So from here, if you wanted to continue the example, you could take the total weight of the hatch, whatever number that would be, the total weight, of the hatch, whatever number that would be, and the buoyant force, and compare them to, and if the buoyant force is greater than the weight of the hatch, then that means that it would float. And then right here, I just included a photo diagram of the volume displacement by the hollow submarine hatch. It has the X and Y, it's on an X and Y graph with the integrals from -1 to 1, the equation on the bottom, and the inner and outer rings forming the washer-shaped shape. Now onto my final thoughts. So finding the volume by the disk/washer method is really useful in physics because it precisely calculates how much water a hollow object displaces, which in our case was a hollow submarine hatch. This is especially important because when designing, it is specifically important when designing stable buoyant objects, and which for example which was the hatch. And then below I have other pictures that also contribute and could be where physics can be used to figure out if those float. Now here in the last slide I have my source cited, and in the description I'll also have the other articles with the links of the articles from where I got my definitions, as well as the PDFs for the source cited. Thank you so much.